All right, this is Unit 5, Lesson 6, Inverse Relations and Functions. Our lesson essential question is, how can you find the inverse of a function and verify the two functions are inverses? At the end of this lesson, you'll be able to represent the inverse of a relation using tables, graphs, and equations. All right, example 1. Represent the inverses of a relation. So, what is the inverse of the relation represented in the table? X is the independent variable, Y is the dependent variable. Recall that a relation is any set of ordered pairs x comma y, where x is the independent variable and y is the dependent variable. An inverse relation is formed when the roles of the independent and dependent variables are reversed. So all I do is I switch the x and y's. Okay. So this relation is a function. Here's my inverse. I switch the values in the columns for x and y. The relation is not a function. We order the pairs based on the new independent variable. So you can see that I have two values for 1, and they go to different places. So it's not a function. If an inverse relation of a function f is itself a function, it is called the inverse function of f, which is written f to the negative 1 of x. All right, so let's try it. Identify the inverse relation. Is it a function? Okay, so here's my original, negative 1, 9, 0, 7, 1, 5, 2, 3, 3, 1, 4, negative 1. So all I'm going to do is I'm going to switch my x and my y coordinates. So 1, 0, 1, 2, 3, 4. I have no x values that are the same, so I can check my answer here. They just ordered them. Okay. So yes, it is a function. The inverse relation is a function. Okay. So you're just switching the x and y. If none of the x values are the same, then it probably is a function. Just double check. So if this were 1, 3, like it is, and this were 1, 2, then it wouldn't be a function. Okay. All right, example 2, find an equation of an inverse relation. So let f of x equal x squared. How can you represent the inverse relation of f algebraically? So f of x equals x squared, where y equals x squared, so I flipped them, so x equals y squared. So y equals the absolute, or plus or minus the square root of x. So the inverse of f can be represented algebraically by the equation y equals plus or minus the square root of x. So let f of x equal x squared. How are the graphs of y equals x squared and y equals plus or minus the square root of x related? Okay. So here is my x squared. Plus or minus the square root of x is right here, so the red one. The range of f is y is greater than 0, so the domain of the inverse relation is x is greater than 0. The inverse of f is not a function. Notice it doesn't pass the vertical line test. So the graph of the inverse of f is the reflection of the graph of y equals x squared across the line y equals x. So let's try it. Let f of x equals 2x plus 1. Write an equation to represent the inverse of f. So I'm going to rewrite this as y equals 2x plus 1. Remember, an inverse is I just flip my x and my y values. So I can rewrite this as x equals 2y plus 1. Now I solve for y. So I have x minus 1 equals 2y, and then y equals x minus 1 divided by 2. E, how can you use the graph of f to determine if the inverse of f is a function? Explain your answer. So the graph of f is a line with a slope of 2 and a y-intercept of 1. Reflecting the graph of f through the line y equals x results in a line with slope of 1/2 and a y-intercept negative 1/2. Since the line is not vertical, it does represent a linear function. Okay. So originally my slope was 2, then my slope became 1/2 with a y-intercept of negative 1/2. That's where I got all that information from. Okay. All right, example 3, restrict a domain to produce an inverse function. Consider again the function f of x equals x squared. Under what domain will the inverse relation be a function? So I identify the problem points. So the inverse relation is not a function since it would contain the inverse of these 2 points, 4, -2, and 4, 2. For the inverse to be a function, all of the duplicate y values would have to be eliminated from the original function. I restrict the domain of f to be x is greater than or equal to 0. So if a function has 2 x values for the same y value, its inverse will not be a function. You can restrict the domain in many different ways to create a function that will have an inverse that is a function. So here's my original. Here's my reflection point. When I reflect it, so y is the inverse. Remember the square, it's the square root function. So we're only using the positive values. The graph of the inverse function of f is a reflection of the graph of f of x across the line y equals x. The inverse relation of f of x is x squared is y equals plus or minus the square root of x. If the domain of f of x equals x squared is restricted to x is greater than or equal to 0, then the inverse is the function defined as f to the -1 of x equals the square root of x. All right, let's try it. Find the inverse of each function by identifying an appropriate restriction of its domain. So I have f of x equals x squared plus 8x plus 16. So this can be rewritten as x plus 4 squared. So this is a graph of a parabola. Has a vertex at 0, at -4, 0. So I want to restrict the domain of f to x is greater than or equal to -4. Then f to the -1 of x equals the square root of x minus 4, where x is greater than or equal to 0. So again, I got this by substituting, I'll bring it down here. So this would be y equals x plus 4 squared. So I want to flip them. So I have x equals y plus 4 squared. So I'm going to take the square root of both sides. Okay, so this is the square root of x equals y plus 4. So I get the square root of x minus 4 equals y. Okay, for b, f of x equals x squared minus 9. So this is going to be, this is a parabola. So again, graph is a parabola, has a vertex at 0, -9. So I'm going to restrict the domain of f to x is greater than or equal to 0. Okay, so then I'm going to switch them. So y equals x squared minus 9. So this is x equals y squared minus 9. So x plus 9 equals y squared. So this gives me the square root of x plus 9 equals y. So f to the negative first power equals the square root of x plus 9, where x is greater than, greater than or equal to negative 9. All right, example 4. Find an equation of an inverse function. Find an equation of the inverse function of f of x equals the square root of x minus 2. So the graph shows that no horizontal line intersects the graph in more than one point. When the graph is reflected over the line y equals x to produce an inverse, there will be no vertical line that will intersect the graph more than once. Since the inverse will pass the vertical line test, the inverse relation will be a function. Use the graph to identify the domain and range of f and f to the negative 1 power. So in this case, the domain is x is greater than 2 and y is greater than 0, greater than or equal to 0. So I'm going to flip them. So the domain becomes the range and the range becomes the domain. So f to the negative 1, x is greater than 0, and my range is y is greater than or equal to 2. So I switch the roles of x and y and solve for y. So y equals the square root of x minus 2 becomes x equals the square root of y minus 2. I square both sides to get x squared equals y minus 2, and then I add 2. Okay, so the inverse of f of x equals the square root of x minus 2 is a function, and f to the negative 1x equals x squared plus 2, where x is greater than or equal to 0. You can verify this on the graph. The graphs of f and f to the negative 1 are both functions and are reflections over the line y equals x. I want to find an equation of the inverse function of f of x equals negative cube root 4x. So the graph shows that no horizontal line intersects the graph in more than one point, so the inverse relation will be a function. So I flip my x and y values. So in order to solve for y, I have to cube both sides. So I get x cubed equals negative 4y. Divide both sides by negative 4. So I get y equals negative x cubed over 4 for all real x. You can verify this on the graph as well. So red was my original, blue was my new one. All right, so let's try it. F of x equals 2 minus the cube root of x plus 1. So I'm going to sketch the graph of f by dragging points on the graph and verify that the inverse will be a function and write an equation for f to the negative 1 over x. So let's see. I've got a couple of different points here. So 7 plus 1 is 8. 2 minus 2 is 0. So 7, 0 is one of the original points. 0. Okay, so when x is 0, x is 0, y is 1. Okay, so there's one of the original points. So I'm going to flip them like this. Okay, so it looks something like that. So negative 1, 2. So again, this was sketch the graph of f by dragging points on the graph. So again, you can check. So 7, 0, negative 1, 2. You can substitute a couple points in here. Okay, and then I want to verify that it'll be an inverse. So I have y equals 2 minus the cube root x plus 1. So this becomes x equals 2 minus the cube root of y plus 1. So I need to cube both sides. So x cubed equals, actually I want to do x minus 2 let's see. So I'm going to do the cube root. I'm actually going to move. I don't like dealing with negative numbers. So x, y plus 1 plus 1 equals negative x plus 2. And we're going to cube all of this. This gives me y plus 1 equals negative x plus 2 cubed, and then subtract 1 from that. So that's what my function looks like. So, and then no horizontal line intersects the graph of f in more than one point. So the inverse of f is a function. Example 5, use composition to verify inverse functions. What is the inverse of f of x equals 2x plus 5, and how can you verify this? So again, I flip them. So y equals 1/2 x minus 5 halves. So the inverse of f is g of x equals 1/2 x minus 5 halves. You can verify this with function composition to be inverse functions. F of g of x equals x, and g of f of x equals x. So f of g of x equals f of g of x. So 2 times g of x plus 5. So 2 times 1/2 x minus 5 halves plus 5 should give me x, which it does. And g of f of x is g of f of x. So 1/2 times your f of x minus 5 halves. So 1/2 times 2 plus 5 minus 5 halves. So x plus 5 halves minus 5 halves is, of course, x. Since f of g of x equals x and g of f of x equals x, the functions f of x equals 2x plus 5 and g of x equals 1/2 x minus 5 halves are inverses. You can also verify by looking at the graphs of the function. The graph of y equals 1/2 x minus 5 halves is a reflection of the graph of y equals 2x plus 5 across the line y equals x. The two functions f of x equals x squared plus 5 and g of x equals the square root of x minus 5 inverses of each other. So again, I'm going to take the composition. So f of g of x and g of f of x and see if they equal x. Okay. So f of g of x, I substituted my g of x, the square root of x minus 5, into my f of x equation. So square root of x minus 5 squared plus 5, which gives me x minus 10 times the square root of x plus 25 plus 5, which gives me x minus 10 to the square root of x plus 30. This tells me right then and there that there can't be inverse functions of each other because they don't equal x. Since neither composition of functions results in the identity function, the functions are not inverses. All right, let's try it. Use composition to determine whether f and g are inverse functions. So f of x equals 1/4 x plus 7 and g of x equals 4x minus 7. So I'm going to take f of g of x equals f of 4x minus 7, which equals 1/4 times 4x minus 7 plus 7. Okay, so 1/4 times 4 is x. 1/4 times 7 is negative 7/4 plus 7. So this equals x minus or plus 21/4. So they are not inverses. Okay. For b, f of x equals the cube root of x minus 1 and g of x equals x cubed plus 1. So f of g of x equals f of x cubed plus 1. So then I have the cube root of x cubed minus 1 minus 1. So that gives me cube root. Oh, plus 1. Plus 1. Yeah, that makes sense. Gives me x cubed, which equals x. And then g of f of x equals g of the cube root of x minus 1 equals the cube root of x minus 1 cubed plus 1 equals x minus 1 plus 1 equals x. So they are inverse functions. All right, example 6, rewrite a formula. A sculpture artist is making an ice sculpture of Earth for a display. He created a mold that can hold 4.5 liters of ice. What will the radius of the ice sculpture be if he fills the mold all of the way? The volume of a sphere is calculated using the formula V equals 4/3 pi r cubed. I rewrite the formula to find the length of the radius. So I'm solving for r. So I get r equals the cube root of 3/4 pi v. Since a liter is a measure of capacity or volume, it can be expressed using cubic units of length. When you take the cube root of an expression involving volume in cubic units of length, the units of the result will be the correct units to describe length. 1 liter is equivalent to 1,000 centimeters cubed, so 4.5 liters is equivalent to 4,500 centimeters cubed. So r equals the cube root of 3/4 pi times my volume, which is 4,500 centimeters cubed. When I solve this, I get approximately 10.2 centimeters. So the ice sculpture mold will have a radius of about 10 centimeters. Rewriting the equation to show r in terms of v is similar to finding the inverse. In effect, you're exchanging the roles of the dependent and independent variables. In the original equation, you can see how the value of v depends on the value of r. In this form of the equation, you can see how the value of r can be determined by and depends on a given value of v. All right, so let's try it. The manufacturer of a gift box designs a box with length and width each twice as long as its height. Find a formula that gives the height h of the box in terms of its volume v. Then give the length of the box if the volume is 640 centimeters cubed. So I'm finding the volume of a box. So a box volume equals the length times width times height. Okay. We're told that with a length and width each twice as long as its height. So 2 times the height times 2 times the height times the height equals 4h cubed. And that equals v. So now I want to solve for h. So v equals 4h cubed. So v over 4 equals h cubed. So the cube root of v over 8 over 4 equals h. Now I want to substitute the value I was given for volume, 640 centimeters. So 640 divided by 4 equals h. So 640 divided by 4 is 160. So h is approximately 5.43 centimeters. So the length is double that, is about 10.86 centimeters. Okay. So concept summary, inverse functions. To find the inverse of a function, exchange the roles of the independent and dependent variables. So with tables, I just switch the columns. In algebra, I exchange the roles of the independent and dependent variables, solve for the new dependent variable. So I switch y equals y and x, and I solve for y. In graphs, I reflect the graph across the line y equals x. If needed, I restrict the domain of the original function to find an appropriate inverse for the function, especially when I'm dealing with quadratics. So anything that's squared to the fourth, so anything that looks like a parabola shape, we're going to probably have to restrict the domain, otherwise it won't be a function. So composition verifies inverses. So the inverse of f of x equals x, and the inverse of f of x equals x. And that is the end of Unit 5, Lesson 6.